So, okay, in the engineering thermodynamics, today we are going to see various gas laws, equation of state, ideal gas processes on PV and TS diagram. So, let's start today's video. So, all these gas laws are based on some particular process, just like a Boyle's law. This is our first law. Boyle's law is based on the constant temperature process, where we kept the temperature constant. So according to Boyle's law states that the absolute pressure of a given mass of an ideal gas is inversely proportional to its volume if the temperature of the gas is kept constant. So if temperature is constant, then the absolute pressure of that ideal gas system is inversely proportional to volume. It means if I increase the volume, pressure will reduce. If I decrease the volume, pressure will increase. So one quantity get reduced, so second quantity will be increased. So it is inversely proportional. That is Boyle's law. So initial state, suppose P1, V1. Now the volume is increases, so pressure will decreases if I kept the constant temperature. So I get different pressure, different volume. And this curve showing the path from state 1 to state 2. And it shows that there is change when temperature is constant, but change is according to Boyle's law. And Boyle's law states that pressure is inversely proportional to volume. If I remove the proportionality sign, then I get PV equals to constant. And if I apply this Boyle's law, PV equals to constant, this is the actual statement of Boyle's law. If I apply this statement to our condition, state 1 to state 2, so our process will be P1 V1 is equals to P2 V2 is constant. This is a Boyle's law. Now, second is Charles law. Charles law is based on a constant pressure process, and it states that the volume of a given mass of an ideal gas or ideal gas system is directly proportional to its absolute temperature if the pressure of the gas is kept constant. That means pressure, if I kept the pressure constant, then volume and temperature are directly proportional. If I increase the temperature, volume will increase. If I decrease the temperature, volume will decrease. So suppose I kept one weight, so pressure experienced by the gas is same until I reduce or increase the weight. This is the initial condition I plot as a state 1. If I provide a heat, so due to heat, there will be expansion of gas. But still gas experience the same pressure. That means that we kept pressure constant. After expansion, we observe the property change in terms of temperature and volume, but pressure is same. We can plot this on PV diagram. So we get a constant pressure line, horizontal line. That is a process 1 to 2. So what is Charles law? Charles law states that volume is directly proportional to its absolute temperature if pressure is constant. If I remove the proportionality sign, so it is V upon T equals to constant. And for our condition, our process 1 to 2, so it will be V1 upon T1 is equal to V2 upon T2 is a constant. Now the third law, Gay-Lussac law, it is based on constant volume process. And it states that the absolute pressure of a given mass of an ideal gas is directly proportional to its temperature if the volume of the gas is kept constant. If volume remains same, so pressure and temperature are directly proportional. If increase in temperature, so pressure will increase. So this is our system. If I heat it, so definitely there will be expansion of gas. If I provide a stopper, now there will be no piston movement, so volume remains same. So suppose this is initial condition P1 and P1. Now even I provide a heat, temperature rises. If temperature rises, so definitely pressure will rise, but there will be no change in volume. So volume remains same. So Gay-Lussac's law statement, it is said that pressure is directly proportional to temperature when volume kept constant. If I remove the proportionality sign, so P upon T is constant. And for our condition, whatever be the process we said, that is 1 to 2. For this, if we apply Gay-Lussac's law, so it becomes P1 upon P1 is equals to P2 upon P2 is a constant. So these are three basics law. Next, Avogadro law. What it says, it states that equal volume of different ideal gases at the same pressure and temperature contain the same number of molecules. It means, suppose for the same volume, we have suppose 1, 2, 3, or 4 different gases, but all gases must be the ideal gas. It should not be a combination of one is ideal gas, one is a real gas. No, all gases should be the ideal gas. In that case, for the same pressure, same temperature, and same volume, all different ideal gases occupied in that volume having the same number of molecules. Different gases having different molecular weights for the same volume, it having different masses, but the number of molecules will be same if they belongs to same volume, pressure and temperature. Since the molecular weight M, capital M, refers to relative mass of individual molecules, and it follows that the different ideal gases at the same pressure and temperature having equal volume contain the same number of molecules. So remember, Avogadro law says about the same number of molecules if the volume, pressure and temperature are same for different ideal gases. How to calculate the number of molecules? So number of molecules can be calculated by total mass of gas divided by molecular weight of that particular gas. Total mass denoted by small m and molecular weight of that particular gas is denoted by capital M. So total mass divided by molecular weight, so we get the number of molecules N. Now suppose there are three gases, ideal gas 1, ideal gas 2 and ideal gas 3. And three gases having the same pressure, same temperature, same volume. So P1, V1, T1, these are the conditions for all three gases. Now suppose first gas, ideal gas 1, suppose total mass is 14. I am not putting the weight unit here, but suppose it is 14 kg. So mass is 14 and its molecular weight is 2. So number of molecules will be M divided by capital M. So accordingly, it is 14 by 2. So we get number of molecules 7. So in this volume, there will be 7 molecules of ideal gas. Now suppose ideal gas 2 is a different gas, so its total mass will be different. So its mass, total mass is suppose 49. Molecular weight is different. In first case it is a 2, but the second case it is 7. So number of molecules will be 49 divided by 7. So total number of molecules will be again 7. So same volume, same pressure, same temperature, different gas, but number of molecules will be 7 again. Third gas, it might be possible its mass is something different, molecular weight is something different. But when we calculate for same pressure, volume, temperature, then third ideal gas again showing the same number of molecules, 7. So this is the Avogadro law. So Avogadro law says about number of molecules are same for same volume, same pressure, same temperature for various ideal gases. Remember, ideal gases should be there. It is not hold good, it is not remain true if there is a mixture of ideal gas, real gas, or different kind of combinations. It is only for ideal gases. Now we will see ideal gas equation or equation of state. So we come to know about ideal gases, its laws. Now we will check out what is the ideal gas equation or equation of state. Many times it is asked in your oral exam that what is its significance. So for ideal gas, the ideal gas equation or equation of state represent actually the relationship between pressure, volume and temperature of that gas. So how pressure, volume and temperature interrelated with each other. If one parameter is increased, then what is the effect on seconds? So that relationship is explained by this equation of state. Suppose one piston cylinder arrangement is there. Very carefully, because many times it is asked in written exam also. So we are going to plot the condition on PV diagram. Initial condition, pressure, volume, temperatures. Now we are talking only for PV diagram. So we will take P1 and V1. So this is our first state. Now if I move inward that piston, so gas will get compressed. So definitely its pressure will change, volume change, temperature change. So on PV diagram, I can say that pressure is increased, volume is reduced. So I can plot state 2. And if I join the process, whatever be the process, suppose first time it follows according to Boyle's law. So suppose A is there. Second time it is follows Charles law. So path will be different, suppose B. Third time it follows the Gay-Lussac's law. So path will be C. So it might be possible that it acquires a different path to achieve the same state 2. So according to law which is followed to acquire the second state. But there is, it is very difficult to identify or calculate numerically the exact path equation. If it is hyperbolic, we have some equation. If it is elliptical, we have some equation. But in between hyperbolic and elliptical, we don't have the curvical path equation. So it is not possible to get an equation, mathematical expression to calculate this. So we simplify this. How we simplify? Our system follow from state 1 to state 2. It might acquire path A, path B or path C. But we can, for simplicity, we can calculate that our system follow first constant pressure path 1 to D. And then after it follow path D to T, constant volume path. And we know very well how constant pressure process is there, what is the work done, what is the constant volume process, what is mathematical expression. So it becomes very easy rather than going with this unknown, undefined curvical path. So we follow that. State will same 1 to 2, but we will follow our well-known processes 1 to D constant pressure process and D to 2 constant volume process. So this analysis can be done by these two processes. So it is possible to change a state 1 to state 2 rather than A, B, C path. We can go with the constant pressure 1 to D and D to 2 constant volume process. Now suppose first process is a constant pressure process 1 to D. So we will use that particular law, PVT is equals to constant. This is very general equation. Now as the pressure is constant, so if I shifted pressure C1 upon P, it become another constant, that is capital C. So constant pressure process, we get the mathematical expression that is V upon T is a constant. Now we are talking for state 1 to D, horizontal process 1 to D. So we can write this V1 upon T1 is equals to Vd upon Td. And what is the value of Vd? So Vd is equals to V2. We can see that V2 and Vd is same. So we can replace Vd is equals to V2. So we get V2 upon Td. Now what is the value of Td? Because Td is the unknown factor. So if I rearrange, so I get that Td is equals to V2 upon V1 multiplied by T1. This is equation 1. Once I reach to point D, then I acquiring a constant volume path, that is V2 2. And for constant volume process, again the general equation is PVT equals to C1. Now this time volume is constant, so I will shift this volume to second side. It becomes C1 divided by volume, and it gives another constant, that is C. So our final form will be P upon T is constant. This is for constant volume process. Now for our case, the process is from D to 2. So we can say PD upon TD is equals to P2 upon T2. Where we can write PD is nothing but P1, constant pressure process. So PD is nothing but P1. So we will replace PD in terms of P1. So again unknown is PD. So we will calculate what is the value of TD. So TD is P1 upon P2 multiplied by T2. This is our equation 2. Now equation 1 and equation 2 both having the TD value. So as left hand sides are same, so definitely right hand side will be same. So we can say V2 upon V1 multiplied by T1 must be equal to P1 upon P2 multiplied by T2. Now we have to rearrange this. So we are just rearranging. So after rearrangement, we found that P1 V1 upon T1 is equals to P2 V2 upon T2. This is the final form we receive. And this can be said that P1 V1 upon T1 is equals to P2 V2 upon T2 is equals to constant. If it is equals to constant, so generalized form will be PV upon T is constant. And this is given a relationship between pressure, volume and temperature of that particular system. So this is called equation of state, a very general generic manner. Now we will see the different form. So 8 now we received the general form is PV upon T equals to constant, where P is pressure, V is volume of gas having a total mass M. So how we calculate the total volume? So total volume is specific volume multiplied by mass of gas. So it becomes total volume. T is a gas temperature and C is a constant. Now for unit mass, where mass is 1. So for unit mass, when mass is 1, so we can say PV, but this V is a specific volume. So P specific volume divided by temperature is equals to R. In this case, when we are talking about unit mass, the constant C is replaced by capital R, and this capital R is known as characteristic gas constant. When 1 kg of gas considered, then constant of equation, that capital C is written as R and known as a characteristic gas constant. Whenever we put characteristic gas constant, so remember PVT, that V stands for specific volume, volume per unit mass. Now each gas having its own value of characteristic gas constant. If it is a argon, R value is different. Helium, R value is different. Carbon dioxide, R value is different. CO, R value is different. So each gas is having its own characteristic gas constant value. Now consider mkg of gas. Till now we are considering per unit mass of gas. Now it is suppose mkg of gas is there. Hence multiply both sides by m. So we get P V specific volume multiplied by mass of gas divided by temperature. Right hand side mass multiplied by characteristic gas constant. Now here we know that specific volume multiplied by mass is nothing but total volume. So we can replace that. So PV upon T is MR. And very well known form of this equation is PV is equals to MRT. So remember, whenever it is said that PV is equals to MRT, that time V is a total volume, not a specific volume. Because already we multiply by M, mass of the system. So PV is equal to MRT, where M is the mass of that system, R is characteristic gas constant. P pressure, absolute pressure, V is volume, and T is temperature. Now unit of this characteristic gas constant. So we know that pressure is the basic unit is Newton per meter square, volume measured in meter cube, temperature basic unit is Kelvin, and mass it is in kg. So we can put all the units of these parameters except capital R. So to find out the unit of capital R, we shift everything, and wherever it is possible, we deduct that particular term and rearrange our unit. So we come to know that characteristic gas constant having a unit Newton meter per kg Kelvin. Newton meter can also be replaced by joules. So it is also says that joule per kg Kelvin. This is a basic unit. Whenever characteristic gas constant kept in kilojoules, so during simplifying we have to put the value in terms of joules. For air, it is a standard value 287 Newton meter kg per kg Kelvin, or you can say 287 joule per kg Kelvin. But many times in terms of kilojoule it is given. So in terms of kilojoule, so it is 0.287 kilojoule per kg Kelvin. This is for air. Remember, I am talking about a characteristic gas constant. So R value is different for different gases. Now there is another term, that is universal gas constant. So we know that ideal gas equation PV is equal to MRT, where V is the total volume. Now according to Avogadro laws, number of molecules is mass upon molecular weight of that particular gas. So mass will be a product of number of molecules multiplied by molecular weight. So we can replace mass by Nm, number of molecules, and molecular weight. This time PV is equal to NMRT, where N is number of molecule, capital M is stand for molecular weight. So M is replaced by N and M. Now if I shift this number of molecules N on left hand side, so it become P V upon N. Now V upon N, it means volume per unit molecule, and volume per unit molecule is known as molecular volume. Just like a molecular weight of per molecule, in the similar manner volume of per molecule is called as a molecular volume, and it is denoted by V, that is small v raised to the power 0. So PV0, that is molecular volume, is equal to capital MRT. Now this time capital MRT. So remember, there are two equations in terms of MRT. PV is equals to MRT. First equation, small m, that means it is mass. PV0 equals to MRT. V0, that means V raised to the power 0, that is a molecular volume. So in this case, this M stand for capital M, that is molecular weight. Now our rearrangement says that PV0 upon T is nothing but MR, molecular weight of that gas and characteristic gas constant. And this product of molecular weight of that particular gas and characteristic gas constant value is known as universal gas constant. So again, R raised to the power 0, that is R0. So we come to know PV0 upon temperature is equals to R0. And in this case, what is the R0? So R0 is universal gas constant. And simply R is characteristic gas constant. Now universal gas constant having a value 8314.3 Newton meter per kg mole Kelvin. Now what is the requirement of universal gas constant? So there are number of gases and number of gases having their own characteristic gas constant value, that is capital R value. And it is very, very difficult to remember all the values. For air, we know that 287, it is a standard value. But for each and every gas, it is not possible to remember its characteristic gas constant. So to simplify this difficulty, we use a universal gas constant, and universal gas constant having the same value for all the gases. So universal gas constant having 8314.3 for all the gases. Now if it is same for all the gases, then how we are going to get a different values for different gases? Because universal gas constant is in actual is nothing but having a relation with characteristic gas constant is equals to universal gas constant divided by molecular weight. So from this, no need to remember individual characteristic gas constant value. With the help of universal gas constant, we come to know what is its value. Now the last portion, 9th slide is there. Specific heat of gas, it is very well known. There are two specific heat. Constant volume and constant pressure. What is the specific heat? The amount of heat required to rise the temperature of 1 kg of substance by 1 degree of temperature. So we are providing some sort of heat, and with that amount of heat, suppose unit mass of the system rises its temperature through 1 degree temperature, then that particular amount of heat is known as specific heat. Now this specific heat can be calculated M specific heat multiplied by delta T. But there are processes, sometime it is constant volume process and sometime it is constant pressure process. So these specific heat are again defined on the basis of constant volume, that is called CV, and on the basis of constant pressure it is known as CP. Constant volume process, so volume remains same, so whatever be the heat added, it is going to utilize in change in internal energy. So constant volume process, CV can be defined as delta U upon delta T for constant volume process. But constant pressure process, there is change in volume. So CP, specific heat at constant pressure, is defined as change in enthalpy divided by change in temperature at constant pressure process. So remember, when volume is constant, so total heat is utilized for change in internal energy. If pressure is constant, so total heat will be utilized to change in enthalpy. There is a work also. So another, that is a ratio of Cp upon Cv, and that Cp upon Cv, ratio of constant specific heat at constant pressure to the specific heat at constant volume, is known as adiabatic index, that is gamma. And gamma value is 1.4 for diatomic gases, just like air and all ideal gases, and for especially monoatomic gases, gamma value is 1.67. So remember, gamma is a ratio of specific heat at constant pressure to constant volume. Now the 10th number slide, constant volume process. On PV and PS diagram, already we know that this animation many times it is shown. So what happened when we kept volume constant? So stopper is there, so PV T, where volume is same, so PV and TS. State 1 is shown. When heat is provided due to stopper, it cannot be moved, so pressure will rise and temperature will rise. So on PV diagram, we get a rise in pressure, that is constant volume, but temperature rise as heat is added, so entropy will increase, so we get a curvical path. So this is constant volume process. So remember, for constant volume process, vertical path for on PV diagram and curvical path on TS diagram. This is our representation for constant volume process. This is a work done. Volume is same, so total heat supplied is utilized only for rise in internal energy. Now the next is constant pressure process. It is on PV and TS diagram. So if we are not removing weight, so system experience the same pressure. Now suppose heat is added, so gas will expand and it reach to second state. If I am going to draw it on PV diagram, as pressure remains same, so we get a horizontal line, but curvical line on TS diagram. Because heat is added, so definitely entropy will rise. Entropy rises, temperature rises, so we get a curvical line. So this is our constant pressure process on PV and TS diagram. Work done. So definitely there is a change in volume. So PdV work is there. Heat is added, so there will be change in internal energy also there. So our equation Q, that is first law of thermodynamics, it is Q is equal to work done plus change in internal energy. And after simplifying, we come to know that what happened to this system, it become change in enthalpy. Already we applied the first law of such systems. Now the second last slide, when temperature is constant. So if I kept the temperature constant, so pressure and volume will interact with each other and inversely proportional. But temperature is constant, so on PS diagram we observe that there is no change in temperature. T1 and T2 is same. And this is work done when constant temperature. We already use this application of first law. Now the last, second last is polytrophic process. Now many times it is observed that how to draw the polytrophic process. This is constant pressure, constant volume. Some animations are missing there. For constant pressure line will be like this. Constant volume line will be like this. This is adiabatic process. Adiabatic process, constant entropy process. This is constant temperature process. This is constant entropy process, adiabatic. On this is constant entropy process. So remember, when we are talking about a PV diagram, so constant pressure horizontal line, constant volume vertical line, then after constant temperature PV constant, and after constant temperature there is another curve line below this PV constant, that is adiabatic. When we are talking about a TS diagram, so adiabatic having a constant entropy process, so vertical line, constant temperature isothermal process horizontal line, after horizontal line constant pressure process curve, then constant volume pressure, constant volume curve. Now where is the polytropic? Here PV raised to the power 1, here PV raised to the power gamma. Gamma for air it is suppose 1.8, it is a standard value. So polytropic index lie in between 1 and 1.4. If it is 1, then it is follow PV equals to constant. If polytropic index is 1.4, it will follow PV raised to the power gamma constant. So it is always in between that PV is equals to 1 upon PV raised to the power n is the constant. So by mistake it is here, actually your curve will should be here 1 to 1.4. Polytropic work done. There will be application of first law to the polytropic work done. In polytropic work done, there is a work done as well as change in internal energy. We are just conclude here because time is over and your next lecture is there. So polytropic work done, we often that the final application of first law of thermodynamics, Q is equal to mCV in whole bracket this polytropic index minus gamma, polytropic index minus 1 multiplied by change in temperature.